Welcome students, myself Dinesh, working as assistant professor. Dear students, in this session we can solve the numerical problems regarding interference of light. Dear students, the first problem is the distance between two virtual images of a slit formed by a biprism is 0.3 millimeter. If the fringes of width 0.59 mm are formed on a screen placed at a distance of 30 cm from the slit, calculate the wavelength of light used. First, read the problem carefully. First, write down the given data, and think it on what phenomena this problem is based on. See here, this problem is based on the phenomena of biprism. Here, the distance between two virtual images of slit formed by a biprism is 0.3 millimeter. That means it is the distance between the distance between the two slits, virtual slits, that is d, small d, 0.3 millimeter is given. That means d equals 0.3 in 10 raised to minus 3 meter. If the fringes of width is 0.59 millimeter, means that is the fringe width beta is given 0.59 into 10 raised to minus 3 meter. And screen is placed at a distance of 30 centimeter from the slit, means that is the capital D. This is the distance between screen and the slit. Calculate wavelength lambda. For this one, you can use the formula. Fringe width in case of biprism is given by lambda into capital D upon small letter d. Therefore, for wavelength, you just rearrange this formula. Then lambda equals beta into d upon capital D. Then you substitute the above data in this formula. We get, and further simplification and calculation, you get 0.59 into 10 to the power of minus 6 meter. This is the wavelength of light used. Let us see the second problem. Interference fringes are produced by Fresnel's biprism in the focal plane of a microscope, which is 1 meter from the slit. A lens is introduced between biprism and microscope. If the separation of the images of the slits for the magnified images is 4.5 millimeter and the same for the diminished image is 3 millimeter, find the fringe width for a wavelength of light 5893 angstrom. For this one, here it is also based on the Fresnel's biprism. Here the width of the slits, virtual slits, not given here. It is given indirectly, that is by giving D1 and D2. Here D1, that is 1 meter from the slit. Capital D is 1 meter. That is the distance between virtual slit and the screen is 1 meter. If the separation of the images of the slits for magnified image, it is written as D1. Let it be D1, that is 4.5 in 10 raised to minus 3 meter. And diminished image is D2, that is 3 millimeter. 3 millimeter is converted into SI unit, that is 3 into 10 to the power of minus 3 meter. Lambda is given 5893 into 10 to the power of minus 10 meter. For this one, you can calculate D, the distance between the two virtual slits, that is square root of D1 into D2. This is equal to square root of 4.5 in 10 raised to minus 3 into 3 into 10 raised to minus 3. And further calculation, we got 3.67423 into 10 to the power of minus 3 meter. For calculation of fringe width, you can use the formula beta equals lambda into d upon small d. That is equal to, you can substitute the value of lambda and capital D value and substitute for d small d. On further calculation, you can get the beta will be 1.6 into 10 to the power of minus 4 meter. Next problem is, in a biprism experiment, the eyepiece is placed at a distance of 1.5 meter from the source. The distance between the virtual sources was found to be 7.45 in 10 to the power of minus 4 meter. Find the wavelength of light if the eyepiece is to be moved transversely through a distance of 1.9 centimeter for 20 fringes. For this one, it is also based on the biprism experiment. For this one, you can use the fringe width formula beta equals lambda d upon d. Here, he asks you to calculate the wavelength of light used lambda. For this one, you can rearrange this formula for lambda, that is equal to beta into d upon capital D. Here, eyepiece is placed at a distance 1.5 means this is the distance between the screen and the slit, that is capital D, that is 1.5. You can substitute for capital D 1.5. The distance between virtual sources small d is given 7.45 in 10 to the power of minus 4. Then you can find the wavelength. On substituting all these values in this formula, you can get lambda equals 4718 angstrom nit. Fourth one, a parallel beam of sodium light of wavelength 5890 into 10 to the power minus 10 meter is incident on thin glass plate of refractive index 1.5 such that the angle of refraction in the plate is 60 degree. Calculate the smallest thickness of the plate which will make it appears dark by reflection. Dear students, by reading this problem, you can think it on what phenomena it is based. Here this problem is based on the thin film interference. For this one, you know that the condition for darkness is 2nt cos r equals m lambda. Here he asked about the smallest thickness of the plate. For the least thickness, smallest means least thickness is m equals 1. For least thickness m equals 1, where m equals 1, 2, 3 and so on. For least thickness m equals 1, put it 1. Therefore 2nt cos r equals lambda, where t is the thickness of the glass plate. Therefore, on rearranging the above the formula for finding the thickness of the plate, therefore t equals lambda by 2n cos r. Here lambda is given 5890 into 10 to the power of minus 10 here upon 2 into n means refractive index of the given medium, that is glass plate, that is 1.5 into cos r. R is angle of refraction, R is 60 degree. On further calculation of this one, we got 0.3 into 10 to the power of minus 6 meter. That means 0.3 micrometer is the answer for above problem. Fifth one, a thin layer of colorless oil is spread over water in a container. Here the refractive index of water is given 1.4. If the light of wavelength 640 nanometer, it is the wavelength of light used, that is 640 nanometer, lambda is given, is absent in the reflected light. What is the minimum thickness of oil layer? For this one, you can got the solution like this. Let T be the thickness of the oil layer spread on water. For minima, he asked what is the minimum thickness. For minima, we know that the thin film interference, in the thin film interference, that is given by the formula 2nt cos r is equal to m lambda. For minimum thickness, we take n equals 1. We take n equals 1. Therefore, T equals lambda upon 2n. Lambda upon 2n. Sorry, here it is not n. N stands for refractive index. Here by mistake it is written as n. This is m. M equals 1. Therefore, minimum thickness, here by putting m equals 1, the formula becomes 2nt cos r equals lambda. For minimum thickness, T minima equals lambda by 2n. For minimum thickness, cos r is equal to 1. It is taken as cos r is equal to 1. Therefore, lambda is 600 nanometer divided by 2 into n. Refractive index is 1.4. On multiplication of 2 into 1.4, it becomes 2.8. This is equal to 214.3 nanometer. This is the solution for the above problem. Next one is, interference fringes are produced by monochromatic light falling normally on a wedge-shaped film of cellophane whose refractive index is 1.4. Here, interference fringes are produced by monochromatic light falling normally on a wedge-shaped film of cellophane whose refractive index is 1.4. The refractive index of cellophane is given, that is the thin film. The angle of wedge is 22nd of an arc. Here the angle of wedge is given theta, 22nd of an arc, and the distance between successive fringes is 0.25 centimeter. Distance between successive fringes is given 0.25 centimeter. Calculate the wavelength of light. For this one, you can use the formula beta equals lambda by 2n theta. This is based on the wedge-shaped film. Here for this one, in the above problem, the angle of the wedge is given 22nd of an arc. Just you convert this one into radian. For conversion of an arc, second of an arc, just you multiply these things. That means 20 by 360 into pi by 180. Pi by 180 is the conversion of second into radian. This is equal to, on further simplification of this one, we get 9.69 into 10 to the power of minus 5 radian. Here the refractive index is given, n equals 1.4. Beta is given 0.25 in 10 to the power of minus 2 meter. Here distance between successive fringes, that means beta, that is in 0.25 centimeter, make it in SI unit, 0.25 in 10 raised to minus 2 meter. Find lambda. For this one, you can use the formula beta equals lambda by 2n theta. Here, for calculation of wavelength, you can rearrange this formula for lambda, that is equal to beta into 2n theta. This is equal to, for beta is given 0.25 in 10 raised to minus 2 into 2 into n, refractive index is 1.4, into theta is 9.69 in 10 raised to minus 5 radian. On further calculation of this one, you got lambda. The wavelength of light is 6.783 in 10 to the power of minus 7 meter. On illuminating a wedge-shaped air film by a light of wavelength 6000 into 10 to the power of minus 10 meter, 20 fringes are formed in 10 mm width. Calculate the angle of contact. Here this problem is also based on the wedge-shaped film. For this one, here the wavelength is given lambda. Here 20 fringes are formed in 10 mm width. Indirectly, the beta is given. calculate the angle of contact theta. For this one, here the data is lambda is given here 6000 in 10 raised to minus 10 meter. Beta, 20 fringes are formed in 10 millimeter width. That means 10 millimeter width divided by number of fringes, width by number of fringes, 10 by 20 into 10 millimeter means it is in SI 10 to the power of minus 3. Millimeter is converted into meter. And further calculation of this one, you got 0.5 into 10 to the power of minus 3 meter. Then find theta. Use the formula theta equals lambda by 2 beta. Lambda is given here, divided by 2 into beta value substituted here. You got the final answer is 123.32. That means it is in the radian 6 into 10 raised to minus 4 into 180 by pi into 60 into 60. Then it becomes 123.32 seconds. Radian is converted into second. For conversion of second, just you multiply 180 by pi into 60 into 60. 60 minutes into 60 seconds. Then you got 123.32 seconds. And further, you can convert into minutes and second. Here 120 second means 2 minutes. The remaining is 3.32 seconds. This is the final answer. Next problem is, in an air wedge experiment, the distance between successive fringes is 1.09 into 10 to the power of minus 4 meter. Calculate the thickness of the object kept between the two optically plain glass plates forming the air wedge. If the length of the wedge is 3.7 into 10 to the power of minus 2 meter and the wavelength of the monochromatic light illuminating the wedge is 5.893 into 10 to the power of minus 7 meter. On reading this problem, here easily you can find out the solution. This is based on air wedge. For this one, you can use the formula D equals L lambda by 2 beta. L lambda upon 2 beta. And further, you can substitute the data for this formula. Here length is given. Length is 3.7 into 10 raised to minus 2 meter is given here, into lambda is given 5.893 in 10 to the power of minus 7 meter upon 2 into beta is given. Beta is 1.09 in 10 raised to minus 4. This is the distance between successive fringes. Distance between successive fringes is nothing but fringe width beta. That is 1.09 in 10 raised to minus 4. And further calculation of this one, you got 1 into 10 raised to minus 4 meter. This is the value, thickness of the object. Next problem is on Newton rings. In Newton ring experiment, the diameter of 15th ring was found to be 0.590 centimeter and that of the 5th ring was 0.336 centimeter. If the radius of plano-convex lens is 100 centimeter, compute the wavelength of light used. On reading this problem, you can easily identify the solution. It is based on Newton rings. You know that the diameter of 15th ring, is given. That is, let it be dm, diameter of 15th ring. M stands for 15, 0.590 centimeter. Diameter of 5th ring, that is dn, 0.336 centimeter. The radius of plano-convex lens is, that is R, capital R, 100 into 10 to the power of minus 2 meter. Use the formula lambda equals d square m minus d square n upon 4r into m minus n. And substituting these datas in this formula and further calculation, you got lambda equals 5880 angstrom. Here m minus n means m stands for 15th ring, n stands for 5th ring. 15 minus 5, that means 10. You can, for m minus n, you can substitute the value 10, and then finally you get the wavelength of light is 5880 angstrom. 10th one is, given the diameters of two successive bright rings in Newton rings experiment, using the wavelength of 5890 into 10 to the power of minus 10 meter as 0.02 meter and 0.0202 meter. Calculate the radius of curvature of the plano-convex lens. Here it is also based on the Newton rings experiment. For this one, you can use the formula R is equal to radius of curvature, R is equal to d square m minus d square n by 4 lambda into m minus n. Here dm is given 0.0202 meter. This is diameter of mth ring. 0.02 is diameter of nth ring. Here m minus n, that means 1. Two successive bright rings, that means m minus n is equal to 1. You can find out R. Lambda is given. You can use the formula, you substitute all the data in this formula, and finally calculation, and calculate it. The radius of curvature of the plano-convex lens will be 3.41 meter. In a Newton rings experiment, the diameter of 10th dark ring due to wavelength of 6000 angstrom in air is 0.5 into 10 raised to minus 2 meter. Find the radius of curvature of the lens. For this one, you can use the formula R is equal to d by 2 whole square upon m lambda. Here, for dark ring, you can use the formula for dark ring condition is d by 2 whole square upon m lambda. Here d is given 0.5 into 10 raised to minus 2 meter. Wavelength is given 6000 into 10 raised to minus 10 meter. Find the radius of curvature of lens. Here for m, you can substitute 10. On further calculation, you got the final answer 1.04 meter. Next one is, if the diameter of the mth ring in Newton's ring by reflected light changes from 0.3 to 0.26 centimeter when air is replaced by a transparent liquid, find the refractive index of the liquid. It is also based on the Newton rings experiment. For this one, for air, here there are two conditions. Refractive index, for air, the diameter is 0.3 centimeter. For liquid, the diameter is given 0.26 centimeter. Then he asked to find out the refractive index of liquid. For this one, you can use the formula d square m equals 4 r m lambda divided by mu, refractive index. On substituting the values of the data given here, dm in bracket, that is A subscript A stands for the diameter of the ring in air. This is the diameter of ring in liquid. You got, on further substitution and calculation, you got the refractive index of the liquid equals 1.33. Here for this one, you can use the formula like d square m for air is equal to 4 or m lambda upon mu a. For liquid, d square m L equals 4 or m lambda upon mu L. On comparing these two equations, finally you got this formula, and on further substitution and calculation you got refractive index of liquid is 1.33. Next problem is, in moving mirror M1 of Michelson's interferometer through a distance of 1 mm, 3000 fringes are counted. Calculate the wavelength of the light used. On reading this problem, you can easily identify on what phenomena the problem is based. Here it is based on the Michelson's interferometer. For this one, you can use the simple formula. That is, it is one of the application. Michelson interferometer is used to finding the wavelength of light used. The first application, that is lambda equals 2x upon n. Here x is nothing but the distance moved by the mirror m1, that is x. X is 1 millimeter. You can just convert millimeter into meter, that is 1 into 10 raised to minus 3. That is, it is not 10 raised to minus 1, it is 10 raised to minus 3. 2 into 1 into 10 raised to minus 3 divided by n. N is the number of fringes counted, that is 3000. That is equal to, on further simplification, further calculation, you got 6666 angstrom net. This is the final answer. It is a very simple problem based on Michelson interferometer. 14th one. For two consecutive maximum distinctness were found to be 0.6443 mm in a Michelson's interferometer. Find the difference between two wavelengths. The mean wavelength is 5893 into 10 to the power of minus 10 meter. On reading this problem, you can easily identify on what basis this problem depends on. Here this problem is on second applications of Michelson's interferometer, that is difference between the two wavelengths. For this one, you can use the formula d lambda equals lambda square by 2x. Here where lambda is the mean wavelength is given, 5893 into 10 raised to minus 10 meter is given. You can substitute here, that is whole square divided by 2 into x. 2 into x is the distance moved by the mirror, that is 0.2945 into 10 to the power of minus 3 meter. Here in the above problem, the distance is not written here. You can just correct it. 0.2945 into 10 raised to minus 3, that is meter, is the distance moved by the mirror, that is x. On further calculation, you got 5.896 into 10 raised to minus 10 meter. Here for this one, x, for value of x, d is given here, 0.9388 minus 0.6443 into 10 to the power of minus 3. Here one term is missed here, that is maximum distinctness were found to be 0.6443 mm and 0.9388 mm. Make it correction, and finally and substitute here, we got this answer. 15th one. Calculate the distance between two positions of the movable mirror in a Michelson's interferometer corresponding to two distinct consecutive fringes. If two closed lines have the wavelength 5893 in 10 raised to minus 10 meter and 5896 in 10 raised to minus 10 meter, you can calculate the distance between the two positions of the movable mirror. For this one, you can use the formula d lambda equals lambda square by 2x. For this one, you can rearrange the formula for finding the x, that is the distance x. That is x equals lambda square by 2 into d lambda, and further substituting the datas and values, you can got the answer 5.790 into 10 to the power of minus 4 meter. You can find out the mean wavelength lambda by adding these two wavelengths divided by 2. Just you add these two values and divided by 2, you get the mean wavelength lambda, and use the same formula, above mentioned formula, in the problem number 14. You can rearrange this one for x, finding x. You can got the answer 5.790 in 10 raised to minus 4 meter. That's all. Thank you.